So in terms of the lab is, I mean, I'm sure it was difficult in the sense of this is your first problem. You'll look back and trust me, this will be like easy. You'll wish that there's a kinematics or a constant velocity problem on the AP exam. I mean, and I really mean that. You will wish for it. So it's interesting how people grow in a physics class. So all that said, how many people did not complete it and have questions? So wait a second. Everyone completed it and no one has questions. You want to do the lab? Okay. Well, I want to defer the lab until the end of the block at the very least. You wait. That's right. And part of the reason why is because, in my opinion, I don't want to spend too much time in non-accelerated motion. Because really, you know if you belong here based upon accelerated motion. Like, if it's like, oh my God, this is crazy, you belong here. If this is like, oh my God, I can't do this, I don't want to do this, I will not do this, then you might want to drop down a level. And generally speaking, I think everyone here, by and large, belongs here. But it's important to get to this point because I don't want, as my students told me last year, they don't want to be sold a bag of false goods where they get through kinematics, they get through the second part of kinematics, and then they get to forces, and it's like, boom. They get dropped by forces. And so I don't want to drop anyone. I'm a peaceful guy. So, anyhow, any questions? Questions on the lab question? Questions in general? Meta questions, yes.
Are you going to go over this as a question, or is it just what we're going to find in the lab?
I think I would want you to, on some level, to find that it gives you an accurate representation. I think I'll go over it once I grade it. And this is why I'm a little hesitant to actually collect it today, because I think I might use it for an SGO, which means I would want to collect it from every single person. And so, that way, rip it apart and figure out what to do. The grading of it, don't worry about, because on some level, the grade that goes into Power School, I'll be pretty lenient on. And part of the reason for that is you've never dealt with this type of question before. How many people have seen these types of questions before? Where it's like a design a lab question. I think those in AP Chem had to do something like this last year, right? Yeah, maybe like at some level, at least either on the exam or at some point they dealt with a lab design question. And this is hard. It's not easy. It's not easy to do. And it's very easy to pick it apart. Like, for instance, how many people did multiple trials? Anyone? No one did multiple trials. Okay. That's cool. So, all right, where did we leave off? If I'm correct, we left off with acceleration. And I defined acceleration. And if I'm right, I was in a hurry, right? So average acceleration. What's the definition of average acceleration? Yes? Change in velocity over the change in time, delta v over delta t. And now the question is, what type of velocities are these? These are instantaneous velocities, meaning like this is vf, this is vi, This is TF, this is TI. And we just jump straight, just go to the point, Khalil. This is V of t minus V of 0 over t. All right? Notice, what did I assume here? That TI is 0 and TF is t. So now here's a question. And this is kind of a killer question for you guys. Why didn't the Greeks discover acceleration? Talk about it with each other. Try to figure out why the Greeks or the Romans did not discover the concept of acceleration. Give you a minute. Try to postulate it. They understood velocity. They understood velocity. Or they understood the notion of velocity. All right? All right, I think someone's got it. I think someone gets it. So what is it? What do you need in order to actually measure acceleration? Okay, so you need the concept of velocity, but what do you need to measure the velocity at? Yes. You need. So what about time? Okay, and what type of measurement of time do you need? Think about this. What you need is a device that measures what? Time in what? Very, very small intervals. You need some accurate time measuring device. Think about it. Is average velocity a difficult thing to measure? Why? Why is average velocity a fairly easy thing to measure? You have some type of timekeeping mechanism. It doesn't have to be terribly accurate, right? And what do you measure? Where something is. What about instantaneous velocity? How do you measure the instantaneous velocity of something? Like, for instance, let me give you an accelerated motion that you're totally familiar with, at least in terms of your experience. How do you find the velocity? Here. Yes. How do you find that velocity at that point? I mean, but that's giving you an average velocity. In other words, you need some very, very sensitive timekeeping mechanism that is accurate to a level that you can actually make these measurements. Well, that wasn't invented until around the time of Galileo. And so this gives you some insight how the discovery of mechanical equipment aids in the discovery of theory. So it was the pendulum clock that made a huge contribution to the ability to keep time. Trivial or not trivial, it's not obvious that this was, that this was the major contributor. This was the thing that you needed. And just to give you an idea, the Greeks were brilliant. I mean, and the Romans were too. The Romans, what they did with architecture, from a scientific standpoint, and engineering, to a large degree, hasn't been replicated. Like, for instance, anybody know about the Colosseum? All right, so the Colosseum, inside the Colosseum, they had naval battles. What does that mean? They filled it with water, right, in real time, had a naval battle, right, in front of an entire audience, and then drained it of water for the gladiators to fight immediately afterwards. Think about how insane that is. Is there any stadium that can do it now? No. So it's not necessarily, I mean, part of this is not necessarily that lack of engineering know-how. I mean, they have the engineering know-how. But did you think they did 2,000 years ago? I mean, how many people thought they did 2,000 years ago? Like, how many people were surprised by that fact? I mean, so 2 people? Well, tough crowd. So anyhow, uniform acceleration, or excuse me, average acceleration. I guess a good place to start as any with average acceleration is to talk about the scenarios of acceleration. So let's go through this. So the 4 scenarios of acceleration in one dimension. The first one, well, before I even do this, let me ask you this question. If I call this the positive direction, and I accelerate in the positive direction, that's called an acceleration, correct? If I accelerate in the negative direction, therefore that must be a... Is that correct? No. That is called a negative acceleration. We're not going to use the term deceleration until... I'm going to try to avoid using that term until you guys are sufficiently comfortable with all of kinematics. So it might be a unit or 2 before I even talk about that term. And you'll see me, I'll actually explain it today, but I really want to avoid using it. So let's actually go through the scenarios. So scenario 1. Let's suppose your acceleration is greater than 0, and your initial velocity is greater than 0. What happens to your final velocity? Your final velocity will increase, decrease, or stay the same? Yes. It will increase. What will happen to your speed? Anyone? Yes? Increase. And what will happen to your position? That's correct. So this is the trivial case. And there's an equally semi-trivial case. Number 2. In other words, acceleration is greater than 0, initial velocity is greater than 0, final velocity is increasing, speed's increasing, position's increasing. Acceleration is less than 0. Initial velocity is less than 0. What happens to the final velocity? Yes? Decreases. Hello, sir. Welcome. Speed? Was it? It increases. Position? Decreases. Nice. So does everybody understand these? What does this mean? This means if I'm starting moving, then I accelerate, right, in the positive direction, what's going to happen? My speed's going to jack up, and my position is going to increase, and of course my velocity is increasing by the very nature that my acceleration is positive. In the second case, if my acceleration is negative, that means that I'm accelerating in which direction? That direction. And that my initial velocity is negative, means that I'm initially moving in this direction, and then I accelerate, and what happens? My final velocity becomes more negative. My speed, which is the absolute value of that final velocity, becomes more positive. But I'm moving further and further away in that direction, which means my position is decreasing. So those are the easy scenarios. Now let's deal with the more difficult scenarios. So the next scenario is A is greater than 0. The initial velocity is less than 0. What happens? Pick someone. Anyone. Close your eyes and point somewhere. My man. What's your name? Was it? Tommy, what you got? Start with the easy one. Acceleration is the change in over the change in time, right? So if the acceleration is positive, that means velocity is changing how? Positively, that's right. Velocity is increasing. So that's the easy one. Next one. Yeah. Do you know everyone here? Why not? All right, I'll pick a random person. Powers. What happens to speed? It increases. You sure? Anyone else? Let's think about what happens. The acceleration's directed this way. I'm initially moving this way, right? So what's happening as I'm moving this way? My velocity is getting what? My velocity is increasing, which means it's getting closer and closer to what value initially? 0. That's right. Since my velocity is getting closer and closer to 0, all right, that means my speed must be decreasing till what happens? Yes? That's right. Till v equals 0, then the speed increases. Yes? So you'll see this shortly. Before I explain this right now fully, you'll see it shortly explained. So just hold on that. Yes? What's happening is the acceleration's positive, right? So that means the change in velocity is positive. But the initial velocity is, I guess I'll explain it right now. The initial velocity is negative. What does that mean for the initial velocity to be negative? That means it's going which way? It's going this way. So this object's going this way, right? What's happening as it's going this way? Let me actually try to do this. Right? Notice my initial velocity is in this direction. Where is my acceleration directed? That way. What happened as a result? I slowed down and I stopped. But if that acceleration kept going, what would I start doing? Accelerating like this, back that direction, at increasing speed. So, what happens to position? You can talk about it with each other for a second. All right, what do you got? Yes?
I wanted it to decrease until it equals 0 and then start increasing.
Correct. Because the initial velocity is negative, that means which way is this object moving initially? In the negative direction, which means its position decreases until v equals 0, and then afterwards it increases. Don't zone out right now. Seriously, do not zone out. This is so incredibly important. Because this is the beginning of the concept that is the core concept of how objects move in the entire course. There is no bypassing accelerated motion. If you don't understand it, you will be forever lost. So you have now the next couple weeks to begin understanding it. And the best time to start is now. So the last scenario is A is less than 0. VI is greater than 0. What happens? It's the reverse, but think it through.
So yeah, it would be constant. Because even when he's slowing down, it's still getting less.
All right, so what do you got? VF is A is less than 0, which means the velocity is changing which way? Negatively, which means the final velocity is? Or not necessarily negative, but it's decreasing. Okay? What happens to the speed? Be careful. The speed decreases till v equals 0, and then it increases. What happens to the position? It's hard to picture in your head, right? One of the reasons why it's hard to picture in your head is because acceleration is so hard to envision. Yes? Very good, Powers. X increases till v equals 0, and then it decreases. And why is that? Because initially, where is the velocity directed? In the positive direction. So you're initially the velocity is directed in the positive direction, but you're being dragged back this way, right? So until you reach a stop, and then what happens? Then your position starts decreasing. Yes? When v equals 0, is that when it changes direction? Very good question. So now, very, very good question. So now we go to a physical example that both that question gets addressed and hopefully sheds light on your question as well. So uniform acceleration is very difficult to envision. The best example you could use is the one that you're most familiar with. And the one that you're most familiar with is acceleration of gravity. So here's a ball. We need to come to some agreement. What are we going to call up and what are we going to call down? Yes. Up is? What do you want to call up? Be careful. What are we calling it? Positive or negative? We're calling up positive for now. Do we have to? No. But right now, to maximize your familiarity, we're calling up positive. Okay? So what I'm going to do is I'm going to throw this ball up. But before I do that, the question is, where are we setting our origin? Do you want to set the origin here? You can. I wouldn't recommend it, though. How about I set the origin at the floor? Okay, I'm going to set the origin at the floor. I don't need to. I can't stress this enough. I don't need to put the origin there. I just want to maximize your familiarity with the physical situation. So the origin's here. So therefore, the initial position is, I can't hear you, positive. The initial position's positive, When I throw this up, the initial velocity is positive. So now, I'm throwing it up. And just don't worry about when it bounces. Just look at the trajectory before it hits the ground. What happens? The initial, tell me which scenario is this? Talk to each other. Which scenario is this? All right, so does anybody feel like they have a full explanation for this? Let's start. So the initial position's positive, the initial velocity is positive, right? What happens as it's going up? So which scenario is this first? This is a scenario 4, definitely. Okay? This is scenario 4. So, it's going up. What's happening to its velocity as it's going up? Yes. It's what? The velocity? Be careful. The velocity is decreasing. Why is the velocity decreasing? Because the acceleration is negative. The velocity is decreasing. Right? What's happening to the speed as it goes up? The speed? Take a look. The speed decreases on its way up until it reaches the top. What happens at the top? It changes direction. What's the velocity at the top? 0. It changes direction, and then what happens? Notice, as it's going up, what's increasing? 1 second. What's increasing? The position. Position's increasing. So the velocity's decreasing, the speed's decreasing, right? Position's increasing. Hits the top, velocity 0. Then what happens? The velocity continues to decrease. Speed increases. Position decreases. Questions?
Why is acceleration negative from the beginning since you're throwing it up to the top?
Great question. My God. Who wants to explain it? Yes.
The instantaneous acceleration from his hand throwing up is positive, but on average it's negative because from the moment after he throws it, it's just the force of gravity going against it.
Okay. So now that is 100% right. Now let me actually give you a less sophisticated answer. We neglect the entire time I'm throwing it. So in other words, the only time that matters is directly after I throw it and right before it hits the ground. That's the only time we're observing. Great answer. Great answer. So in general, with the motion that we're going to be observing and describing, it's after the impulse force, not during it. So once it leaves my hand, what's the acceleration? What's causing the acceleration? And what direction is that acceleration? Negative. And it's constant at all times. So now I'm going to ask you a very straightforward question. You're going to hop on Pear Deck. Okay? Are you guys using this in your other classes at all? It's useful, right? I mean, it's not useless. So, whatever, I'll start a new session. Open this up. Invite a class. Come on. And you guys are 1.8. So, anybody listen to any of the videos yet? So in case you want to actually revisit the class, your class is the one that's being recorded. So switch views, projector view, and now I'm going to go here, and now I'm going to ask a question. Okay, here you go, guys. Here's a question for you. Draw velocity versus time for this. For this scenario. Remember, I'm asking you to draw velocity versus time, not position versus time. All right. I am going to lock it in 5, 4, 3, 2, time. And here they are. Well, did that work? Okay, here they are. So let's see if we have a proper one. Let's see. Not many people labeled their axes. So let's take a look at this one. Is this correct? Yes or no? Why? Yes.
It's not crossing the time axis.
Why? And why is that important?
Because velocity goes from positive to negative, therefore it must cross the zero.
And what does that physically represent?
The place where the ball was first thrown from. I mean,
Keep it good.
because wait, no, I didn't. It doesn't actually. It basically like the point in time it represents.
Yes. What point in time does the yes? What does that represent physically?
When the ball changes direction.
Very good. So in other words, this is incorrect because it has to cross that t-axis. It crosses that t-axis at v equals 0. And v equals 0 represents the point of highest or maximum position, or where it changes direction. So I think the most correct one, I believe the most correct one is it this one, or is it, there's one that is 100% correct. And it's this one. I think it says Brian. Who's Brian in here? So explain. Explain exactly, well, assuming that this has labels, explain why this is 100% correct.
Because it starts with a positive motion, so it's going positive until it hits 0, and continues downwards.
Okay? And so now, did you intentionally make this longer than this?
Yes.
Okay. Why was that longer than that? Because what happened?
The starting point was already a positive area, so it has more distance to cover.
Correct. In other words, because it traveled a much greater distance with its velocity, because it traveled a much greater time with its velocity directed in the negative direction, that means this leg is going to be longer than this leg. And what you were inferring was the area under the curve for the displacement. So we'll get to that in a little bit. Questions on this? Yes? Okay, so speed is something that you're going to have to compartmentalize separate from everything else. The direct connections that we have are velocity to position and acceleration to velocity. Speed works kind of on its own independent plane, where speed is equal to what? The absolute value of the velocity. So what is the speed? How would I describe the speed on here? So how would I draw the speed? So what would S versus T look like for that scenario? That's right. It would look like this. So, and this is why I'm a little hesitant to really stress speed, because it's operating kind of almost independent of the action. It's the absolute value. Right now, what you really need to focus on is the connection between position, velocity, and acceleration. And then once you have that down, then you can focus on speed. Any questions? Unless you have it all down, then you can shuffle the cards. Play as you may. So, now let's actually look at the scenario of, kind of the critical scenario that we're going to be looking at for the majority of this course, which is uniform accelerated motion. Uniform accelerated motion. By the way, you now have enough to completely tackle your homework assignment, the WebAssign homework assignment. And that's due on the 16th at 11:59 p.m. So if you have questions for me, when do you also ask it to me? Not 11:59 p.m. But I give you the whole day in which you have class with me. So if I need to address any particular questions, I can. So uniform accelerated motion. What does this mean? That means if A is constant, what can you say about the average acceleration? Then the average acceleration is equal to what? A. In other words, if A is some constant value, A, the acceleration is a constant value, A, is a constant value of A, then A bar, the average acceleration, is simply equal to A. This is no different than the scenario where average velocity equaled V, for velocity being constant. And so what am I saying here if acceleration is constant? What acceleration am I talking about? Instantaneous acceleration. If the instantaneous acceleration is constant, then the average acceleration is simply equal to that constant. So what's the consequence of this? Well, what does average acceleration mean? Change in velocity over the change in time. What is the change in velocity? It's simply v of t minus v of 0 over t. And so what's the consequence of this? That if I go and write v as a function of time, what do I get? I get v of t minus v of 0 is equal to a times t. And solve for v of t, you get v of t is equal to v of 0 plus at. What is that saying? Anyone? Favo, what do you think that's saying? This right here. That uniform accelerated motion makes velocity a linear function of time. In other words, if you have uniform accelerated motion, your velocity function, your instantaneous velocity, is a linear function of time. So now is the point in time where you ask me, Khalil, show me the money. All right? Show me the money. I've had enough of this nonsense. Show me that this is true. So what do? I go and I find that's not cool. 1 second. Hey, Quinn, do you know where Trent is? Do you know where Trent is?
I mean, 222.
222. Thank you. No problem. These are the things that happen. It only took 15 minutes, and yet in 15 minutes I lost my most precious resource. So, there you go.
Thanks.
No problem. All right. So, show you the money. So what I'm going to do, get out of here. All right. So, I'm going to start off, and I'm going to position this so that it's at the origin. So this is the origin in this coordinate system, right? And now, I'm going to so what do you notice? Well, let me clean this up a bit. I'm going to get rid of that which is just where it kind of loses signal. And I'll get rid of that just to make sure that what we're doing is the period of time in question. Or, you know what, I'll even get rid of that. Notice how readily I get rid of data. Don't be afraid of that. Our devices are not 100%. It's not so much that they're not 100% accurate, but sometimes you get misreads associated with certain complications with the apparatus. So what do you notice here? You have two graphs. One is a velocity time graph, and the other is a position time graph. So what do you notice about the velocity time graph? Yes. Meaning it's uniform accelerated motion. What do you notice about the position time graph? Anyone? Yes. Okay, do you know exactly what would you suspect the relationship between position and time is? Clearly this is uniform accelerated motion. How do we know this? Because the velocity time graph is linear. Question is, what do you suspect the position time graph to be? And it turns out, which you'll see shortly, is that it's quadratic. In other words, that x of t is proportional to t squared. Notice it's not linear. That's a critical observation you need to make. Any questions? All right. So now with that, I want to talk about instantaneous acceleration, and I'll close it for the day. You can do your lab. So, instantaneous acceleration. And if you run out of time for your lab, that's fine. We can carry it on another day. We're going to go through the same process for instantaneous acceleration that we did for instantaneous velocity. And what process did I go through? I first draw some type of graph. Here is v, here is t. And now, maybe I'll make this a little thicker. Here is v, here's t. And here's my graph. So the first question I have for you guys is this uniform accelerated motion? Yes or no? No, it's not uniform accelerated motion. Meaning that this has some type of instantaneous acceleration that's not constant. So, how would I define instantaneous acceleration? Well, the same way I did with instantaneous velocity. Well, if I were to ask you, take 2 points in time, t and t plus delta t. What is the average acceleration on this graph represented by? First time you see it, it looks like a mystery. Second time you see it, it's clear as day. Average acceleration, what would it be represented by on this graph between t and t plus delta t? Anyone? Yes. Yes. What of the line between the 2 points? The slope of the secant line between those 2 points. So I draw a secant line. Here's this secant line. And now we know that the slope of the secant line is a bar. We know it's the average acceleration between t and delta t. And so I go through the same procedure. If I wanted to find the instantaneous acceleration at time equals t, what do I do? Yes? That's right. First I zoom in. First let me expand this. Right? So that is the secant line. And then I zoom in. I'll pan this over, go to 50, or go to 75, maybe pan this up. Okay. And then I'll start drawing secant lines. Notice, so notice this secant line, the delta t went from there to there, and then I can keep going sequentially until I get to the tangent line. And so yet again, what is the instantaneous acceleration? It's the tangent line to what? Instantaneous acceleration is the tangent line to what curve? I can't hear you. Which graph is this? Velocity versus time. So the instantaneous acceleration is the tangent line to a velocity time graph. Write that down. Or in the language of limits, a of t is equal to the limit as delta t goes to 0 of a bar. So, additionally, we can look at the various properties. And it has the same exact structure. If we have v as a function of time, and it looks like this, something like that. Okay, and let's suppose this is your function. So here is v as a function of t. And I were to ask you, where do the maxima and minima occur at? Powers. Oh, okay. Very good. The maxima in this case, the maxima and minima actually occur, the absolute max and min occur at the endpoints. Where do all the other max and mins occur? Yes. Okay, and what is the acceleration at those points? Correct. How do you know that? Okay, that's certainly true. What is the simplest way to describe that, though? If you draw a tangent line through those points, what's the slope of that tangent line? 0. So draw tangent lines. Boom, 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 boom. So there you go, guys. Relative mins and maxes of velocity occur where the acceleration is 0. The instantaneous acceleration equals 0. Similarly, we have other properties as well. Here's v, here's t. If you have the following graph, there's a mean value theorem as well. Remember what the mean value theorem said? That if I have 2 points, TA and TB, what's the average acceleration on this graph? Slope of the secant line. So here's your secant. Okay. Mean value theorem says what? There's a point between TA and TB, called T star, where what's true? There's a point such that the tangent line through that point of the function is equal to what? Slope of that secant line. Ah, that didn't look very good. In other words, the tangent line through that point is parallel to the secant line, meaning the instantaneous velocity, the instantaneous acceleration, at t star is equal to the average acceleration between TA and TB. Any questions? None? All right. So, with that, I want you guys to spend 5 minutes looking at lecture problem 7. And talk to each other, because you're going to need to. All right. Want a piece of advice? Here's your piece of advice. If someone jumps off a bridge with a bungee cord attached, don't follow him. That's the advice. I'll follow up with a second piece of advice shortly. You're not following the piece of advice. You're following the guy. What type of graph is this? Have you seen that yet? No.
They absolutely have to go on. Like, free fall.
You're following the guy. You're following him. All right. So I'm going to, now that most of you are following him, I'm going to give you a hint. Beyond just don't follow the guy. There's one line you should be looking at. Anybody want to know what line that is? It's the A = 0 line. Obvious or not obvious? Draw the A = 0 line.
Positive or negative?
Looking at this, I would say, I'd say up is positive, down is negative. Questions? Questions? Come on, I'm sure you guys are asking questions. 2 more minutes. All right, you got 2 more minutes.
No, this is down. Because he has to fall. So this would actually be down. So he's going down. But this is when he reaches. So there's a point. He reaches 0. There's a point there too that it sort of stops and then.
Oh, so here's what. So this is down. He
Yeah,
jumps.
that's the first
He goes
one.
all the way down, and then he starts. This is him slowing down. His acceleration is slowing down. He gets to 0.
Right.
And then he goes
That's the
back.
part. That's yeah.
This is
So
when he
this
gets. This is him.
Stop following him. Stop following him. Stop following him. You're trying to follow the jumper. That's insane. This is a crazy acceleration time graph. All right, you guys ready?
No.
So how you guys doing? You can be honest. It's okay. That's perfectly normal. Perfectly normal. Yes. Yes. Very much so. There's a reason why. That's okay. There's a reason why I'm saying don't follow this guy. It's crazy to follow this guy and try to understand where he is on this trajectory. We don't have that familiarity. Let's just try to chart it out. So, I think now I'm going to go through this. And I think many of you will be surprised at how simple it is once you abandon the idea that you need to follow him. What does A equals anything above A equals 0 mean? That's called positive up, negative down. What does anything above A equals 0 mean? Yes? That means which means that his velocity is increasing. So watch this. Velocity increases. It's at its highest point. Velocity decreases. I don't care how much it's decreasing by. All I care about is whether it's increasing or decreasing. So decreases, continues decreasing all the way until A equals 0. And right there is his lowest, or its, what would you say? It's highest min, or lowest min, or the most downward. And then what happens here? Increases all the way until here. So now, identify all the points. Yes? Okay, well, notice it's saying upward speed, downward speed. Yeah, that's the reason why I put it in there. Yes? It's so jagged because probably the measuring device is not very accurate. Yes? Local? Local means like the relative maxes. That means that in that area, right? So it's these points that are your local max and mins, or relative max and mins. Yes? Someone here had their hand up? No? Okay.
Well, I was going to ask, from looking at this, would it be possible to tell which min or max was like the highest or lowest?
Not easily, no. Well, you can, but you would need to go to the next step, which is finding the area under the curves. And that's later, but even there it's going to be very hard because it's very jagged. Someone had their hand up here. Anyone? Yes.
So when it's going up, like this way,
Yes.
like right here, this means decreasing.
That means the acceleration is decreasing. But let's not even think about exactly. Let's not even think about what that means. All you care about is anything above, right, means that the velocity is increasing. Anything below means the velocity is decreasing. Right? Because anything above means A is positive. A is positive means correct. Anything A is negative implies velocity is decreasing. Okay. So, with that, and it's a good example, right? This fleshed out. Does anybody have any other questions on this before we hop on pair deck? All right, yes. Oh, so the most positive, the relative most positives are going to be here, 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 right? And the most negatives are going to be on the way up. Here. You could technically say maybe here, but here, here, and here. Questions? All right, nice wiffle ball question. "30 seconds. If the velocity of a car is not 0, can the acceleration be 0? Ten seconds. Five, 4, 3, 2, lock it. The answer is yes. That just means that you are cruising on Route 80 East in a straight line at 60 miles per hour, and you're not hitting that gas. You have a non-zero velocity, and what's your acceleration? 0. That's fine. Almost everyone got it right. Consider the line labeled B in the V versus T plot. How does the speed change with time? 1 minute. Yeah. So, time. What do we have? What does this do? 5. It decreases and then increases. All right, so here's some velocity time graphs. I want you to rank the magnitude of the accelerations. Give you a minute. Act quickly. I'll give you 2 minutes. By the way, when we get back, we've got like 12 pair deck questions to go through. So trust me, by the end of these, you'll have a very solid grounding on acceleration. So what type of graphs are these? Velocity time graphs. How do you find the average accelerations? Slopes. Magnitudes, absolute value of whatever the slope you found is. Later, guys. Which block is this? Yeah, which period's it? 8. So that means this is 8, 5, 6. Got it.